Okay. So, hello everyone. Do you hear me well? Anyone?
Yep. Yep.
Yes, Professor.
Great. Yeah. All right. So, yeah,
Very
welcome
clear.
to. Yeah. So please keep your mics muted. Yes. Hello and welcome to the first lecture in this introduction to quantum computing course. And today, the lecture number one, according to our syllabus, called Introduction to Linear Algebra. Intro to Linear Algebra. And today, we're gonna discuss a linear vector space, the concept of linear vector space. So, unfortunately, quantum computing business is all based on math and especially linear algebra. There is a lot of math here, and the first part of the course will be, about this introduction to the required math. Otherwise, you cannot grasp the rest of the course, the rest of the subject. A good news is that linear algebra in the heart of the most of basically engineering and the most of new concepts and the hot topic in engineering. Artificial intelligence uses linear algebra. Quantum mechanics, quantum technologies, quantum computing, they based on linear algebra. Any sort of communications, any sort of data processing, data storage based on linear algebra. Electric schemes, circuits, like power electronics, all these areas are based on linear algebra. So that's why linear algebra is so important. And good news is that this introduction to linear algebra that we will talk about the next 2 or 3 weeks is a good introduction to the subject. All right, and when we talk about linear algebra, the first concept we mention is linear vector space. So let me color the main concept in red. Okay, so definition: linear vector space. And of course, since this is the preliminary or prerequisite, you're supposed to already be aware at least of the most of this part. So linear vector space. We denote this vector space as this wavy brackets with the name of the space. For example, we can use V. And linear vector space is a collection of all vectors equipped with 2 operations, with addition and scalar multiplication. So the linear vector space is a collection of vectors equipped with 2 operations. And now in black. The first operation is vector addition. addition. It means that if we take any two vectors like v1 and v2, we can take the addition of both, right? v1 plus v2, and this will give us another vector in the same space. All right. So yeah, it's very simple. And the second operation is scalar multiplication.
Professor,
Yes.
I'm sorry to interrupt. We're right up there in red. Does that say vectors equipped with two operators?
With two operations.
Is that the word with preceding the word two?
Yes, sorry. With
No, that's fine. I'm just trying to take notes. That's all.
yeah, my handwriting. Sorry for that.
I can relate.
Yeah, no problem. Yes, and of course, if you got any questions, please feel free to ask. Okay. So scalar multiplication. So suppose we have a scalar alpha. This operation says that we can take a product or multiply a vector from this space by this scalar alpha, and the alpha can be either real or complex number. We will recall the complex numbers and complex functions, I guess, next week. And for example, if
I'm
yeah,
so
this
sorry.
is yeah,
Scalar? Okay.
alpha is scalar. Scalar. Scalar means 1 to 3, 1.2, etc. Just number. And this operation also gives us the vector from the same space, right? How it works? For example, if you have a vector like this, right? Multiplication by a scalar means that we simply scale this vector. For example, we obtain a vector like this. So this is another vector from the same space. And for example, if alpha equals to 0, then we will get 0 times v, right, which is 0, but not just 0, it will be 0 vector. Because when we write expressions like this, we have to have, if you have vector on the left, we must have left a vector on the right. And of course, these operations, they must satisfy certain axioms like associativity and distributivity. Let's recall them. So operations. Let's I guess I wrote this correct. Associativity means that if you have a expression like alpha times beta is another scalar, and times any vector like this, right? And I, for example, can take the product first of beta and v, and then multiply the result by alpha, or I can take first the product of alpha and beta and then multiply the product by the vector v. So the result is supposed to be the same. So this is the the property of associativity. And another one is distributivity. Distributivity means that if I have a sum of alpha and beta and multiply by v, I can first multiply alpha by v and then plus beta by v. So this is just formal mathematical operations. We won't really need them in what follows. Just to refresh. And also at this point, I would also make a note about how we denote this product or multiplication. So here we write this as a dot between the letters, like alpha times v. In the literature, you can also find just alpha v, and we will also use this just alpha v without, skipping this dot. Or sometimes in the literature you can find alpha with dot here below and then v. So all these equivalent forms, depending on the textbook, lectures, this might vary. So yeah, and at this point, let's consider a problem. The first problem. So let's take two vectors. For example, two vectors in two-dimensional space. The number of components of in a vector corresponds to the dimensionality of the space. And saying that the space is two-dimensional means that our vector is two-component at most. So let's say we have two vectors like u with components, say 3 and 1. Right. So we can write the vector as a column of numbers, and each number in this column corresponds to the vector component. We will discuss this in a few minutes today. So this is the first one, and the second vector, let's take 2 and 4, for example. And as an example of a constant, let's take 5, right? So as a problem, let's find, for example, the sum of two vectors, right? So we give an example of this vector addition. So we have two vectors in two-dimensional space, and then can take the addition of two. So it will be, the first one is 3, 1, 3, 1, and then plus the second vector is 2, 4. Right. How we multiply the vectors? We just take the sum of corresponding components, right? So 3 plus 2 gives us 5, 1 plus 4 gives us 5, 2. So this is the result of this multiplication. And one can also write this like 5 times the vector 1, 1. That's also possible, because when you multiply a vector by a number, you basically multiply each component of the vector by this number. And the second one is multiplication alpha times, for example, v. So our alpha is 5, then times our v is 2 over 4, and the result is 10, 20. 10, 20. So this is the new components of the new vector in the same vector, linear vector space that we obtain after multiplication this vector by a number. So the next concept, which I also highlight in red, is the concept of linear independence. Linear independence.
Professor, what does this D stand for?
Definition, or
Okay, got it. Thanks.
yeah. So yeah, putting this D here, I know that this is something important uh, to know, to memory, to remember. So linear independence, linear independence. So linear independence. Let's formulate it this way. So a set of some vectors uh, like in our case v1, v2, up to vn. N is the dimension of our space, right? Basically the number of oh no, sorry, n is just denotes the number of vectors. We can use, for example, okay, n works well. Yeah, so we have a set of different vectors. So a set of these vectors is linearly independent if uh, no vector in the set no vector in the set can be expressed as a linear combination of the other vectors. No vector in the set can be expressed as a linear combination of other vectors in this set. Right. So we cannot, for example, write v1 as a, say, v1 as a alpha v2 plus beta v3 plus etc. up to some gamma vn. So in this case, this vector v1 would be linearly dependent. Linearly dependent. So, for example, let us actually write this as an example. So let's take as an example. Let's take just two vectors, v1 and v2. So by the way, when I'm talking about vectors, sometimes I draw this arrow on top, denoting that specifically that this is a vector. Sometimes, especially when we write or describe the vector as a column or row of numbers, there is no need to put this arrow because we explicitly write the components of the vector. So one easily see that this u, for example, here is a vector. So no need to put this arrow on top. In this case, since we don't specify the components of the vectors, I write these arrows here on top. So yeah, so let's consider two vectors, and if these vectors are linear independent, uh, they are linearly independent if some alpha v1 plus beta v2. Oh, actually, let me write this here. Alpha v1 plus beta v2 doesn't equal to 0 for alpha and beta, for basically any alpha and beta, of course non-zero, for non-zero alpha and beta. So if you take two vectors from a linear vector space, and if these two vectors being multiplied by alpha and beta, and then you take the sum, if this operation never turns to 0, then these two vectors are linearly independent. So it might be tricky to get it. So let's consider a problem here. So problem number 2, right? So let's take two vectors like v1, let's say 1 and 2, and vector v2 with components. Let me take, for example, 2 and 4. So v1 is the vector 1 with components 1 and 2, and v2 is the vector with components 2 and 4. Those of you who had a course on a linear algebra already know the answer. So are these vectors linearly alike? Linearly independent. So let's check that. So to check that, we write alpha v1 plus beta v2 equal or not to 0, right? We have to check that. So for alpha, we write just alpha. Then for v1, we have 1, 2. Then beta, any arbitrary beta. And v2 is 2, 4. So we have a vector on the left. We must have vector result on the right. So this 0 is not just 0. This is 0 vector, as we discussed in the beginning. So it's supposed to be vector with component 0, 0. Vector with component 0, 0. And now I can multiply alpha by first vector, beta by the second vector, and rewrite this as a system, right, by components. So alpha times 1 gives me alpha, plus beta times 2 gives me 2. Beta is equal to 0. Alpha times 2 gives me 2 alpha plus 4 beta equals to 0, right? So from here, from the first equation, I conclude that alpha is equal to minus 2 beta. Okay, so we define alpha in terms of beta, and now I plug in this alpha, which is minus 2 beta, to the second equation, which gives me minus 4 beta plus 4 beta equals to 0. So this second equation cancel out, right? 4 beta minus 4 beta gives 0, so it's satisfied. And we're losing this beta, and we get, as a result, we get alpha equals minus 2 beta. So when alpha equals minus 2 beta, then we satisfy this equation. So this alpha v1 plus beta v2 equals to 0, which means that these two vectors v1 and v2 are linearly dependent. v1 and v2 are linearly dependent. So, so far, it might look like artificial, right? So why we need all these for quantum? So we coming to that point. So next concept we need to discuss is the concept of a space dimension, right? Like we have some sort of a linear vector space, but how to describe the dimension of this space? Is this space of finite dimension or infinite dimension? In quantum mechanics and quantum computing, we use both. We use the space of finite dimension and we use space of infinite dimension. These types of dimension also possible. And quite often we truncate the infinite quantum dimension down to dimension of a finite space of finite dimension. So space dimension. Space dimension. How we define space dimension? So the space dimension is the number of linearly independent vectors that this space contains. So the point is that for the linear space of finite dimension, the number of linearly independent vectors is finite. You will get what it means in a few minutes. So the space dimension is the number of different linearly independent vectors of this space. This space. The number of different linearly independent in this space. Or in other words, it is how many independent directions, how many independent directions or axes there are in this space. In this space. Right. So, for example, so let's consider three-dimensional Euclidean space. So Euclidean space, what kind of space it is? Euclidean space is actually the space we are living in. So Euclidean space is our space. This is the space of all our geometry, and this is the space that we use to describe the things in physics, right? So we usually don't name this Euclidean space by saying just our three-dimensional space. So Euclidean space is our 3D space. It's our 3D space. So when we describe our 3D space, what we do, we know that our space is three-dimensional, right? Because we can move, for example, in a room, we can move along one wall, along another wall, and we, of course, can jump up and down, and this is the third coordinate. So there are three different linearly independent directions. So that's why we need this concept of linearly independent. So we have three linearly independent directions in our 3D space. Traditionally, we name them X, Y, and Z, right? X, Y, and Z. So for these vectors, we can put. I mean, usually we put these orts like E, G, K, right? Or V1, V2, V3. So these three vectors, E, G, K, they are E, G, K vectors. They are orthogonal, meaning that if I move along Y, X and Z doesn't change. If I move along X, Y and Z doesn't change. This is exactly what makes these vectors linearly independent. So these vectors, they are linearly independent. Linearly independent. And how many these linearly independent vectors in our space? 3. That's why our space is three-dimensional. For an ant or a bag on a surface, right? The animal that can jump, for example. For these types of bags, the space is two-dimensional. They can move along one direction, another orthogonal direction, but not up and down. So their space is two-dimensional, but also Euclidean. Two-dimensional space, three-dimensional space. In two-dimensional space, we need two linearly independent vectors to describe the things happening in that space. So now we see that these linearly independent orthogonal vectors, they rather define the directions in space. So we don't need we are not considered in their value or length. We just need to know the direction in the space, which are linearly independent. So in order to define the direction in space, we need to basically normalize a vector by its length. So if for a given vector like vi, some arbitrary vector in our space, we take a model, right? And this model denotes the value or length of vector vi. So this is how we denote the length of a vector. And now if I take this vector vi and divide it by the length of this vector vi, what I will get? I will get the vector in the same direction as vy, but of unit length. So this is unit vector. We traditionally we denote them by I vector, and this is unit vector. So again, we need these unit vectors to define the linearly independent, or in other words, orthogonal directions in a linear vector space. I hope it's getting clear at this moment. So as we have this set of vectors, right? As we have these unit vectors, we can form a set of unit vectors that direct along the linearly independent vectors. And this set is named a basis. So definition, a basis. A basis is nothing but the set of linearly independent unit vectors. So the word unit here is key. Unit vectors we denote set by this wavy brackets EI like this, and this is set, right? So it's a vector E1, E2, all the way up to En. And here n is the space dimension. Space dimension. Space dimension. For example, if our space is two-dimensional, we will have only two basis unit vectors, E1, E2. If our space is three-dimensional, like we used to, we will have E1, E2, E3. If we choose this orthogonal coordinates, these vectors will be I, J, and K. So this E1, E2, E3, they became I, J, and K in three-dimensional space. So let's again consider a three-dimensional space, not necessarily Euclidean, just any space. And actually, let's assume that this space has some arbitrary space dimension. Yes?
I'm sorry. I'm gonna get off on a tangent in a little bit, but I'm wondering, are you gonna make this notebook available later for download? Because sometimes when you scroll down, I'm not able to finish writing everything that you're putting on your board.
So yeah, I can make it like this.
Thanks, I appreciate it.
Yeah, answering your question, yes, they will be available in the Canvas system.
Good deal. Thank you.
Yes, for sure. Yeah, so let's consider an arbitrary space with these orthogonal vectors that are linearly independent. And these unit vectors E1, E2, E3. And let's assume that we have some arbitrary vector in this space. Let's denote it by V. So we have a vector, and we need to describe this vector. Describe this vector means, yes, Alejandro? I see you raised your hands.
Oh, hello. Can you hear me? Okay, now.
Yes.
Is the set, when you do the set of linearly independent unit vectors, do you pick arbitrarily unit set of linearly independent unit vectors, and you have to implement the axiom of choice for this to choose the set, or is the set given and you have to make sure they're linearly independent, and then it forms a basis?
Yeah. So this is very good point. So how one can do this? You can start from one vector, arbitrary vector in the space, and then find by mathematical operations, basically find this
Yeah, you
any,
diagonalize and find the eigenvectors.
yes, you can
Okay.
find other vectors that are orthogonal to the first one.
Mm-hmm.
Why this point is nice? Because as I said, this like, for example, three-dimensional space, right? We can introduce this rectangular coordinate coordinates like this x, y, and z, and nicely describe the coordinates positions of some objects. But at the same time, sometimes it's better to use, for example, cylindrical coordinates. So it will get z the same, but uh, but rho and phi, right, which are another coordinates, and these coordinates will get another unit vectors, basically directed along the change of rho and phi. So this is another coordinate system with other unit vectors describing the same space. We can introduce spherical coordinate system, rho, phi, and theta, two angles and the length. Again, this is the same space that we described, but we use another set of linearly independent orthogonal unit vectors. The same space, but another basis. And yeah, so answering this question, this basis is not unique. This basis, even this rectangular coordinate system, you can choose this and then rotate it in different directions, right? When you do that, you of course don't change the space itself. You just change the basis. You just change the way how you describe mathematically your system. And this is very much exactly what we need, or what we do in quantum. In quantum, as we will discuss in what follows, we have a quantum system. The state of a quantum system is represented by a vector, like this V vector here. And then whatever we do with the quantum system is described by the transformation of this vector, its rotation, its changing in length, and all these operations can be described by the changing in the basis. We will discuss that later, but yes, so very good, very important point is that the basis is not unique. And in fact, in any space, there is an infinite number of different bases. But as we have selected, for example, one vector, we can find the other two linearly independent or orthogonal vectors to the pre-selected one. So as we introduce this space of n dimension and this vector, how we describe this vector, right? So we describe this vector in terms of the projection, this vector to the basis vectors. So for example, this would be projection V3, this would be projection V1, this would be projection V2, projections of this vector on the basis. And of course, this vector can be physical. It can be a state of a quantum system. It can be a velocity of a vehicle. It can be, I mean, something else. acceleration, the force, a lot of things. So it's attributed to the real world, right? But the choice of the basis is arbitrary. So having this vector v, we still can rotate this basis in space, but that of course doesn't change the vector itself. The components of the vectors v1, v2, v3 will change almost arbitrarily as we rotate the basis. But the physical quantity, this v, won't change upon these rotations. So the components of vector depend on the basis, but the vector doesn't. And this is exactly why we bring this concept of vectors to the analysis. So making this projection of the vector on the vector basis, from the basis, we can write our vector as a sum of projections, right? It will be sum over I from 1 up to n. N is the space dimension of projection of the vector vi, v1, v2, v3 times the vector from the basis e I. I would write it like this. So so as I said, this vector v in quantum mechanics, it corresponds to the real state of a quantum system. And when we write the expression like this, it means that we describe this quantum state in terms of other states. Okay, and we often, we all the time write the expressions like this. So speaking about the components of basis vectors, speaking about these basis vectors, we can still write them as columns. For example, E1 would be a column of 1 and then all zeros, okay, down to nth element. So this would be a column like this. So E2, in terms of their projection in the same basis, it would be 0, then 1 here, then 0, 0, all the way down to nth element. And the same way up to En, which will be 0, 0, 0, 0, all the way up to the 1 here on the nth place. Yeah. So this is the components of the basis vectors in this basis, right? Because the projection of the vector E1 on E1 gives you 1 in length, because the vector is unit. It has unit length. And the projection of E2 on E1, of course, is 0, because the vectors are orthogonal. So that's why these components of these basis vectors in the same basis looks like this. And in this basis, our vector v, just v, this vector v will get the projections v1, v2, all the way up to vn. So this is components of the vector. Okay. So at this moment, it's nice to make this definition and introduce the Einstein summation rule. So Einstein summation rule. Einstein summation rule, as you probably No, it arises when we have expressions like this with two indices like VIEI vector, right? So we have these two indices and we sum up all these terms like V1 E1 plus V1 V2 E2 plus V3 E3, etc. So quite often it's I mean, this can be written by skipping this summation sign here. So the expression like this can be written just like VI EI. And when we meet this I twice, it means that we do summation. And when we get this, when we encounter this, we can skip the summation sign just for to make the things tidy and shorter. So it's 7 already. Let me just start talking about the products. And the first one, the product, right? The operations that we can do with vectors in a vector space. So the first one, I mean, after multiplication and product by the scalar, multiplication by scalar, we can introduce inner product. Also known as
number 1.
Yeah, I put number 1. Number 1, inner product, also known as dot product, and also known as scalar product. Scalar. We will consider 3 types of products. And the first one is inner product. So inner product is a operation that allows, that allows you to having 2 vectors. Let's now name them A and B. You have 2 vectors, and in the result you get a scalar. That's why this name scalar product. So the scalar product or inner product or dot product is denoted by this dot between the vectors. Sometimes it's denoted by, like this, A comma B in the parentheses. So if we represent vector A as a summation AI and then the basis vectors EI, which is again the same as AI EI, right? And the same way for vector B. So what we will get? We will get AI EI vector product B J. We need to use another letter because the I is already taken for the summation operation. BJ EJ, like this, right? So we can rewrite this basically just changing the order as AI BJ and then EI EJ. So can we simplify this further? Yes. Let's look at this product EI EJ, and let's think about what it is. So for so let's specify I and J to figure out the the rule. So let's take I to be 1 and j to be 1. So in this case, it would be E1 vector times E1 vector, right? And in components, it will be 1, 0, 0, all the way down. And another one is 1, 0, 0, 0, all the way down. And when we take the product of these two, we have to take the product of, I mean, by component by component. First component by first component, second by second, and then plus. So it will be 1 times 1 plus 0 times 0, etc. So it will be 1. So we notice that E1 times E1 gives us 1. And the same for E2 times E2 and E3 times E3, we will get 1 all the time. But what if we have different indices? For example, E1 times E2, right? So these two vectors will be 1, 0, 0, 0, 0 times 0, 1, 0, 0, 0, 0. So in this case, it will be 1 times 0 plus 0 times 1 plus 0 times 0, etc. So it will be 0. So we conclude that if you take a product like EI times EJ vectors, we will get so-called Kronecker delta. Kronecker delta with indices ij, which is equal to either 1 when I equal j, like here, or 0 when I am equal to j. We can actually frame this and put a star sign. So this is what we get. We get this Kronecker delta. Kronecker delta. So now we return back to this expression. So because of star formula, this one, we conclude that this product of EI, EJ equals to Kronecker AI, BJ, Kronecker, IJ. Kronecker, IJ. And now, if we, for example, consider the product of BJ, Kronecker, IJ, sum BJ over J delta EJ, right? What we get? So this delta is very simple, right? It's equal to 1 when the indices equal, when J equal to, when I equal to J. And otherwise, it's equal to 0 when I am equal to J. That means that all the time when J, or better say when I equals to J, this expression will be equal to beta bi, and in other cases it will be equal to 0. So all this sum is simplified to bi, right? So it's very simple to see. We take the product of the two and take the sum, and all the terms in this summation equal to 0 except for the only one bi. So we can put double star here. So now, because of this double star formula, we conclude that this summation is all equal to AI, BI. Okay. So the formula, the final formula is like this. When we take the inner product of vector 1 plus times vector 2, it will be simply AI, BI. AI, BI. Or I just remind you, we use this Einstein summation convention, but without it, it would be summation over I, AI, BI. Right. For example, for three-dimensional space, for 3D, three-dimensional space, we get this formula that we use to A1 B1 plus A2 B2 plus A3 B3. And the result of this operation is a number. That's why the scalar product. As an example, let's take the product of vector by itself, a times a, which is nothing but a square, the square of vector. We get a1 square plus a2 square plus all the way up to an square for n-dimensional space. And by definition, the length of a vector is the square root. It's the square root of a square, right? Which is square root of a1 square plus a2 square plus all the way up to an squared. So this inner product or scalar product, I would say, is like, I mean, the most important one, because in quantum theory, it allows us to make predictions, or basically it allows us to connect the experiment with the results of calculations. We will discuss that later on, along with the rest of the products we will discuss next time. I think that's good enough for today. So let me stop the presentation, the recording, and we can discuss further the lecture and